does it start? Yay, it did. Okay. So I have to finish up a couple slides from last time. I think we had gotten to this point. Actually, let me back up one just to make sure everybody understood this, the point in here. So we ended with trying to discuss how the intensity changes across an image. If you remember, I said there was two big effects that take place. One has to do with the distance from the source. Obviously, further out on a detector, a flat detector plane, it's further away from the source. So if we were to put spheres going through, the sphere going through the center would touch here, the other one out there would be a larger sphere. So the size effect of that is going to be proportional to the angle, in particular the cosine squared of the angle. Like, that's a pretty direct measurement of just the angles to get them. So, but that's not the only effect we mentioned. There was one other effect besides just the straight distance, which is what this slide is trying to get across here. Does anybody remember what this one was showing us?
Yeah, so the rays are spreading out like a cone and you take a cross section.
Yeah, so you figure when it's coming towards the plane, right? So you can imagine kind of a detector, maybe like the top of this monitor here, right? And when the rays are coming in on it, it's coming in at an angle, which means the actual shape would be like this. So the ray, if this was just one pixel, right? One ray would be hitting here, but it actually spreads that shape out rather than this size to this size, right? So it takes up more area than it should, right? So if I were just to take the direct image size down here and flatten it without scaling, it would be smaller than what it's going to take because the ray's coming in at an angle. So the further away from the origin, the more it's going to spread that out. And that spreading factor we showed is also proportional to cosine. So that means the whole thing is cosine cubed, right? Cosine squared for its distance, and then cosine squared for this kind of spreading function it's trying to show you. This is a picture from the end of the chapter. You're not doing it as a homework problem, but it's one of the possible homework problems that's in there, where this is a cone, or a cylinder, sorry, and you can see it's much brighter and getting dimmer as it goes out. You can see that spread, right? So the origin, like, it's kind of carrying up this way, which means the origin is like right about here. Right? So you can see the closest point spreading out. But this should be pretty much the same. You can see it's much longer. The same exact effect. Therefore, dimmer. Anyway. I just wanted to mention a couple quick things that are on here, because a lot of times we look at a single image and we figure that single image, there's one scale to the image, right? But that's not true. Right? It would be totally true if it was taking a picture of a picture, right? But it's not, it has depth. So consider just the problem, right? It kind of starts there. We've got an X-ray source, a point source. This will be true whether it's a fan beam or a cone beam. Most geometries that we use nowadays are either fan or cone beam. So essentially, this is a reasonable image of what's there, an essentially point-like effect to it. So if we're looking at something, you know, this one kind of gives you an idea why we might consider that geometry. That just kind of shows the points better, right? If you consider this, there's an object, say like, you know, some cube that's along that central axis. When it's going through, it'll hit, right, the front end of the object, and it'll be a smaller projected area. It gets bigger towards the back, right? So if you think about it, that's kind of what I'm trying to get across with this one here, right? Imagine this is the front of the object, you know, at Z1, and Z2 has the back of the object. And I tried to draw that blue line to show those are the same height. It's kind of height profile is the exact same. But towards the origin center, it's gonna take a larger angle to reach that first height, which means it's gonna hit on the detection plane way up higher than the back. So things towards the front of the body are magnified bigger than ones towards the back because of the depth. Right? I mean, it's reasonable when you think about it, but we're gonna go into tomography in a little bit, and that's an effect we have to think about, right? But on top of it, doctors reading x-rays and us figuring out how do we wanna make things have to realize what you're getting when you take a picture is not, a nice, flat, everything's even sort of picture. Now, you could do that by taking a single beam, right? And just taking that beam and just scan across, right, down the next row, kind of like a TV scanner, right? You could get them all nice and parallel then, and you would not have this type of a scaling effect. Why not do that? It removes a big problem.
Time.
Yeah, what does time affect for us? I want you to think about this because this will make sense for us. Okay, but I'm giving you less per area, right? So that is a true point, it does, but since I can, instead of doing it, one short thing but a wider area, more photons, I'm gonna trade off time versus overall width of the beam that's on there, net effect gonna be the same.
The X-ray tubes have really low efficiency, so you're just letting through a little bit.
Yeah, so I really have to get a narrow beam, or I'm overheating the thing, wasting more power. So it is gonna have a power effect on this as a waste, and also commensurately time the machine or the components before they break down from it.
Doctors are, well, I guess they're not, but a lot of hospital staff it's around them, so.
So there's also a personnel cost, right, to people running this equipment, right? I agree with that one too. There's more though. There's a lot when we start to get into this.
The body's gonna move a lot that one time.
That's another one that's very interesting, right? So one is also the annoyance of the patient, right, similar to the previous one.
Yeah.
But movement of the body, right? This affects several different things, right? Some of them are kind of subtle. Imagine for a sec I was trying to, do a quick scan, a very common radiation therapy treatment is for prostate cancer, right? Prostate cancer, where the prostate's located nearby your bladder, therefore build up a fluid in your bladder, and it may be not the most attractive thing to think about, but you have to when you're dealing with medical stuff. Gas in the bowels, which is often commonly associated with a lot of stuff with cancer treatment, will move stuff around down there, right? You're often trying to do an x-ray scan on the day of treatment to verify things before you go ahead and proceed, right? If I were doing something slow like that, while I would get a perfectly flat, non-scaled image, the image would be from drastically different time periods, which means they no longer fit together, right? Imagine if I were doing the same thing for a cardiac study. I'm not even guaranteed I'm going to be in the same cycle in your heart, right? Lots of stuff could have changed. How do I even connect these disparate ideas, right? So you can imagine there's a huge number of these timelines, and we often don't just want 3D CT, we often want 4D CT, right? A time CT as well, so we can take a look at moving areas of the body, right? Yeah.
So over what kind of distances are we seeing this kind of like distortion? Because like are you talking about like you mean the distance between like the front of your ribs to the back of your ribs? Yeah, because your ribs are like curved, right? And so
the relative size of your sternum and ribs in the front will be larger than the ones in the back, right? So particularly if you think about the fact that usually when you're taking that image, you got your shoulders up against the actual imaging plane, so you're going to get a true size of the back ones, and they usually try to put the source, maybe it's like a meter away, something like that. So if you think about the depth of a human chest, maybe a foot, some change, right? So, you know, a third of a meter, maybe it's as far as 2 meters away on the other one. You know, you're talking somewhere between a third or a sixth of the distance to that source is the thickness of the body. This is a non-negligible fraction, right, of what you're dealing with. So, you know, it can cause distortion. You know, we'll have to actually track and we'll consider the actual position each of the rays lie along when we do the inverse for CT scans. You know, but for our purpose here, right, that's, you know, if I was just doing 2D, I still have that problem. Doctors often will look at them, you know, just to, you know, be able to do a quick scan. Hey, I see something weird there. Oh, there's a hairline fracture or whatever else, right? Things that's it's a good question, right? Do we feel comfy with this idea of the relative scaling that goes on?
I have a quick question
Yeah.
about what we do about it. So if we just do a normal X-ray, do we just kind of live with it?
Yeah, pretty much I mean, the image you get out,
Right.
because the doctors are gonna look at this, they actually just give them the Mylar film that was on there
I see.
in most hospital situations.
Okay.
That pass around. As you get newer and newer, we talk about the imaging ones, you could in theory correct that on newer systems. But you would have to make assumptions if all you have is a one-dimensional picture.
Right. Okay.
Right, so if all you have is a picture from one direction, you're gonna probably live with it, or you have to assume a basic model of the person to try to undistort, and that's usually not a practical situation. All right, we feel good? Okay, I want you to also just think a little bit about problems caused by the fact that the source is not ideal. And this will affect some images and there will be some artifacts from it, right? If you assume for a sec, right, you can see that kind of top picture, top left picture, right? I have a true source. The line halfway between the diaphragm and the detector plane, the object projection that's on there, see that little line part way? That's supposed to be the object. So imagine I'm trying to image that line. So you can see on the port source, goes through the diaphragm, there's the upper and lower line that intersects the diaphragm. Those are the first x-rays that are gonna make it out. So that just tells you how big the overall projection is gonna be. We do usually wanna make sure whatever our object is squarely inside the shape, not too bad, but you know, and you get your image. Now the question is, what happens when you start to get to an extended source, right? A point becomes a sphere or things of that sort, right? I think a point it becomes a line, because not our sources are not actually points. So what happens when you actually our source is usually a line, and then we try to truncate the thing, right? Well, now instead I've got this line area. So each point along here, we draw the appropriate cone. Right? So this is just looking at the particular part from the diaphragm, but from the top point of the source creates the larger, right, or the lower down one, right? And then from the bottom part of the source, we get this upper line. That is, right, you know, it's called the penumbra, because you get partial coverage, the same as you would with, you know, a lunar eclipse or other types of things of that sort. You know, but when you look at the effect on an object doing the same exact thing, that kind of penumbra effect that's caused on the edge of the lighting means that they're overlapping adjacent areas for the same exact point in the object. So that's going to cause a blur to, in essence, be affected upon it. Now, you can't remove this, but I can mitigate it. So how might I be able to mitigate this?
Source smaller? Yeah.
Okay, so if I make the source smaller, it definitely will mitigate against it, right? So do you think there's a limit to how small I can make it?
Yeah.
So what do you think affects
Oh, you mentioned how small the electron stream is from cathode to the anode.
Very good, yeah, right? So it's gonna be affected by that. There's an associated heat buildup, right? You get smaller and smaller, more heat concentration is gonna go on. So there is basically, you know, some power, some beam spreading, some basic limitations that are kind of come in that you can't avoid on them. So there is a minimum, but ideally, smaller source is better. Right? Is there anything else I can do? So we consider this, make this one smaller. Yeah, the relative distance, right? You could even say relative to this opening. Right? As I move the source around, that's going to affect how big relatively that penumbra / blur is. Right? So if I were to move it further back, they're going to become more and more parallel. And as they become more and more parallel, the effective width of that is going to become smaller. What's the disadvantage of doing that? Life is a trade-off, right?
Less intensity.
And the lowered intensity, which means I've got to get a more concentrated beam off of them. Ideally, I'd like a more concentrated source beam from it, so I don't just have to throw away a lot of those other x-rays, so I'm not just wasting energy. And effectively life and heat and things on there, right? So source distance, another thing I can control. With trade-offs, what else can I do?
Move your object further.
Okay, so I can move the object. That's going to effectively do that same distance sharing, right? So there's two different distance trade-offs I can do, right? Source to where the diaphragm or where that, you know, both the filter and the collimator are, right? We're just kind of combining it together here, right? I can also consider moving this one. Now, if I move this one back out, you get less and less of the space. And as I do that, I effectively have to shrink the opening. Right, so that I get things more concentrated on them. So the basic geometry you have to consider on this has to do with the relative distances and widths of the objects. Right. Now I can also do one other thing if I want, but this becomes a little more expensive, but sometimes it's worth it. I can also control these by an electromagnetic field. Spread things, right? So there are some ways I can try to affect them on here. That's kind of costly. Usually we do it in different ways, but there are ways I can scan things in that sense. But for a cheaper setup like a 2D one, you're never going to do something like that. So, you know, effectively I have to control those on. Since you can't ignore it, what we're going to do is we'll consider the effect of that point source. You can see they do it effectively through a point hole, you know, to take a look at that, the resulting image that's on there. I can figure out what that transfer function is depending on how far in Z is, and then I consider that for every single point. And then I just can treat it like a blur that hit it. Now that blur depends on Z, which means it'll vary by the depth. Things in the front get blurred more than things in the back. So you're going to get a crisper image the closer it is to the actual detector plane, because you are effectively changing the distance of those images. So if a doctor is particularly concerned, this is why sometimes when they're taking chest x-rays, they'll have some where you got your back against it, but sometimes they'll have you turn around and hunch your shoulders forward and try to conform to it so that you can get a clearer image of the front. What are you trying to aim at? Right? If you're interested in spine, things of that sort, obviously you want back forward. Right? If you're looking at the heart, which is more kind of towards the front, it makes more sense to have the person kind of hunch their shoulders forward onto the plate. Right? Changing the position will change the clarity, the overall quality of the image you can achieve. Does it make sense? Right?
So, is the point hole is on the, like, is it on the emitter or the?
No, so that's not actually, we're assuming a point hole here. because imagine it's one particular point on you. Like I just take a little volume on you, and I want to see what's the effect of it. So this is the source, how it affects that tiny, tiny minuscule point on you, and what is the effective image. And you do that a whole bunch of spots in one shot, right? So they're going to overlap each other and blur. But I can consider the real point was like right there, so it was blurred. Same thing happens for the next point over, and it blurs and overlaps.
So
Right.
when figure C says edge blurring, is that just because they notice it more on the edge?
Well, because you'll see that hardening or sharpness on there. It's technically doing that everywhere. That's what this is telling you.
Right.
It is very easy to see there, and that's what most people are going to comment on or notice, right? There's a couple reasons why. Like, what sticks out the most in your body with an X-ray? Bones. What part of the bones? The edge. Why does the edge show more? There's actually a few reasons here.
Because the density of the material is much more than like the
Very good. That's what a lot of people miss, right? So your bone is not one monolithic thing, right? The outside edge is usually referred to as cortical bone as opposed to the center, which is called trabecular bone. The interior part, for lightness, is kind of more spongy styled, right? Lots of little openings and stuff like that, because you don't get a lot of strength out of it, but you need the stability. But the outer edge, very, very hard, much, much denser. That's going to show up stronger. So the outer edge is going to be stronger. What else happens? Remember we mentioned something happens under the physics? We called it EH, edge, hardening, right? So remember on that BB, it kind of naturally causes this cupping because you don't have a monolithic source. Right? So the associated beam hardening, right, as you're going through a material, you drop off more of the lightweight stuff. So that means if it's just in the edge, it's going through very little of the material, which means disproportionately more of the low energy stuff will make it because it's really thin. Okay? So it's going to look abnormally bright, I guess would be the best way to say it. Right? Because you haven't lost as much of those low energy, which even with a little more depth would easily get knocked out. All right, so you tend to get this cupping that goes on. So it's naturally going to make the edges brighter. And then add to it the fact that bones are denser, so they're going to be a little brighter on that outside edge. Right? You know, even just considering those two, you're going to expect you're going to get a lot of sharpness on. So you would normally expect a very sharp edge to this, but then the blurring takes some of that away. And given the brightness of that, that means it can obscure things very close by too. It's very hard to detect. So we want to be able to correct that as much as possible so you get an accurate image of what's going on there. Make sense? All right. I think this was the last of the slides we hadn't talked about. Yep. Let me switch. So this is today's. Okay. So we're going to start off. We need to do a little bit of description of how we're going to image these, right? So we call it CT. So you ought to know why it's called CT, right? And we're going to 3D. So CT is computed tomography. Tomography, right, comes, it's our root, right? So from tomo, which has to do with a 2D slice or picture of something, and graphy, right? Which has to do with representation. Right? So you're making a 2D representation. Literally, a tomograph is a two-dimensional slice through an object. So if you're taking a picture straight on, the picture you get is a 2D projection. If you have that same source, the slice would be coming through like this on me, right? Now, depending on where your source is, if it's on the top, right, the slice is always going to be, in some sense, the one that's not kind of parallel to the source's, plane. Now, we have names for each of these planes. it's not completely standard, and there are axial directions that go on. So I wanted you to get used to the names that doctors are going to use. The most common one I've always heard are the ones I've listed here: axial, coronal, and sagittal. I've put alternate names underneath them. So axial, if you look on it, cuts this way. Imagine the axis runs from the center of the earth through my head. Right? So that's the axis. So the axial plane is going to be cut so it is tangential to that axis, right? So that's called the axial one. It also has other names, right? Since that plane, what we call the axial plane, is horizontal to the ground, it's sometimes called the horizontal. It is also sometimes called the transverse because it runs side to side, front to back. Right? So that's sometimes known as transverse. I most commonly hear axial. The next one I hear is transverse. This one's been creeping in more and more lately. I think it's because people don't like some of the older names to them. But my personal opinion is just learn the old names. You'll sound much more intelligent when you're talking about them. So, don't rely on the language to simplify. Right? All right. So the next one is coronal, which cuts across this way. Again, the simpler name, I haven't heard any other, so axial and transverse appear very early on. Axial, again, is more common. But horizontal and frontal are more recent ones that come in. There really isn't a competitor in the past. It's always been coronal, slicing this way. Right? So that is just the standard name for that image as you're going in, right? So the coronal plane. The sagittal splits you left to right. All of these planes, the medial version of these is defined as where 50% of the body mass is to one side or the other of the plane. So that's where the medial plane is supposed to be defined as. Now, technically that could be a pain in the butt to find, So often effectively people will measure it from some other relative area and just try to, get you as close to that as possible. But that's the technical definition of the midpoint is 50% of the mass on either side. This gives you a relative image of a brain in those areas, right? Axial, you can see on the left, and you can see the sagittal, right? Kind of cutting across this way, and then the sagittal, you can see the eye socket here in the back of the head. Right? So you've got classic left and right on your coronal. That's kind of where the view planes go. These are standard ways they look at them. You ever got an idea what's going on with these images?
Is this an abnormal image or is it displaying an abnormality?
It's a correct, good image displaying an abnormality on the brain. Any idea what's going on with that abnormality?
Is that what's normal?
That's
Subnormal?
so you can kind of tell from the very light liquid areas and the lighter areas. This is actually it's in the brain, but anyway. I forgot to mention the axes on here, right? So these ones are not hard, left, right. So we then have, there's a difference, and this is why I included the animal. When you go to four-legged mammals, the things change, and you kind of want to understand where they come in. So there's two different names, right? So very often you'll hear, anterior and posterior, right, for front to back. That's the way most doctors I hear talk about them. But you can also call it ventral and dorsal. So ventral literally means towards your belly, right, and dorsal is towards your back. So if you think about for a four-legged animal, right, towards the belly, ventral is down, right? Dorsal towards the back is up, as opposed to the corresponds we had a normal one, right? And anterior and posterior, right, kind of now take the direction towards the head, and towards the rear end. So it is different for four-legged creatures than it would be for two-legged creatures. That's kind of the big difference to get. And so if you hear those words, you kind of have to know which one you're dealing with. There is a huge upswing in veterinary care that's going on. So I've seen more and more. I've actually seen at least pictures of people scanning horses inside a CT scanner. Right? It's a rather unusual setup. You have a CT scanner and you got an anesthetized horse laying on its back with its feet in the air with props on the sides so they can scan them. But if you figure, why might I want to do this? Well, besides people being very emotionally attached to them, if you've got a very good male horse, what you really care about after it's won a couple races is to stud them. All right, so you don't want a problem inside their head to cause a loss of the ability to do stud feeds off them. So they can actually be a huge, they often make more than that than they do off $1 million prize money. So it's a sizable part. So there is actually a larger industry moving towards this. I expect that's going to kick up in a few years. And then obviously we've got superior for us, right towards the head is superior, and then inferior towards the ground. You'll also hear these called cranial and caudal towards the feet area. But you'll notice this changes again, right, towards the cranium is anterior for a foreleg, right, and caudal towards the posterior. Okay, we feel good with those. That gets you your basic coordinate system. And they will measure those, right? Distance, superior, right? When you do the planes, we align them to those planes. So those are the ones we're going to base them off. And you measure the distances on those. Okay, there's a lot of different generations of CT machines. And a bunch of them are still in use. And the majority of explanations are usually given off first generation. So almost all book explanations are first generation because it's just easier. Right? Second and third, even fourth, largely are just going to follow a fan beam type in some sense. Second generation is kind of a weird hybrid, but third and fourth are true pretty much fan beam setups. There are varieties of these, we'll talk in a couple slides, that use cone beam and things of that sort. But it is important to understand we're up to 7th generation, so we'll talk about the other 2 generations or the other 3 generations on the next slide. These ones are largely older generations, although there still are a lot of these still around. Right, 3rd generation. So things are mostly explained here. These are fairly economic and maintainable. They were the state of the art up until the late 80s, early 90s. This one started creeping in the late 80s, early 90s, but it never really overtook this, and this one had certain advantages we'll talk about. The 3rd generation had certain advantages. So they lived on until, in actuality, the 6th generation came in the early 2000s, late 90s, early 2000s, and pretty much every new system is either 6th or 7th generation. All right, so let's just talk about for a sec, 1st generation. The big reason we care about this is it's easy as pie. Remember what we said about that whole scanning situation, or how do we get no artifacts, no scaling problems, right? I just take it and move it along, right? And then I move it down and repeat the same process, so on and so forth, right? So in this case, I just scan all the way across, one at a time, just a single pair, rotate, do the same thing. I do it for as many angles as I want. Classically, this was actually done 1 degree at a time, although there were 1, 2, or 4 degree systems. And then you move down and repeat the whole process all over again. This was overall an incredibly long process. Mathematically, as easy as you can get though. So there are many, many benefits from doing this. that's probably the best thing I could say for it, right? They make the comment it takes up to 5 minutes per slice to scan that. Since most of the other slice things are gonna be like a second or less, it was a ridiculous amount. And if you figured you had to do like, 60 some odd slices, right? Back then you never did that much, but now it's pretty common to have, 20, 40, 60 slices, depending on the area of the body you're looking at. That could really ridiculously ruin your day with the amount of time it takes for that. Right? So, I mean, you say I even did a 30 slice one, right? It's still going to take me 2.5 hours to finish that process. That's a long thing. Nobody can sit that long. So, you're effectively stuck at doing like 6 slices at a time, 30 minutes or so, is usually considered the limit of most people being able to lie in one position. All right, so that's kind of first generation systems. Fairly rapidly, people figured out, well, if I could move this quicker, I'd be able to reduce this drastically. So they just made a fan beam, and effectively, you can see I've got multiple detectors on the other side, so I could spread it out, and now I can just move it a larger chunk and get the same effective thing with less of them. Right? So that process of doing it sped things up tremendously, right? We went from 5 minutes to somewhere around a minute and a half. There is a little more complexity because you've got these overlapping cones, which means you're going to have regional separations because you move, scan, move, scan, move. But the advantage in speed is tremendous. So huge benefit. Even better, what if I could take one whole image at a time? Take an image move. This is why third generation was so awesome. It's usually listed as a second or less. Sometimes people will say half a second. This particular source quotes it at 0.3. As they got later, they got faster with them. It also depends on your detector technology. So, several things were done to kind of make this nice. The picture here, I'm sorry, it's not actually the best picture. It looks too curved. It actually looks like they took this one and took a chunk out of it. It's not true. What you do is you actually base it so that the center is at that focus, and you make an arc, a constant radius centered from that focus. Now, the reason why we do it, think about it for a second, right? What was one of our problems we talked about at the end of the last one?
Was when you have a flat detector plane, you get the cosine.
You get that area, so it's cosine cubed. What happens with this by making them equidistant? It solves both, right? Because your detectors are curved, you don't get that cosine, right, spreading out. And because they're constant distance, you don't get the cosine squared. So it literally takes a cubic distortion and makes it flat constant. That is crazy awesome, right? So there is a lot of advantages to this type of a system. You just have to rotate the two in unison when it goes around, but you're now taking 0.3 seconds, so you're, when you gather those 180 images, it's not going to be too bad. The biggest problem with this one is that actually not here, and we'll see this is where the later generations come in, so I'll get a lot more on this. But imagine how I have to do it, right? So I got the source, a whole bunch of detectors, and they're rotating. How do I connect, right? Because there's lots of detectors, I have to get those signals out. Right? And I have to do it really fast, so I've got a lot of connection cables here. Right? As I'm rotating them, what's going to happen?
The wire was
The cable's going to get wound up around the whole thing. Right? Which means when I go to the next slice, I have to reverse direction to unwind it. And then we have to put drums and everything to wind them back and forth between the two, so I don't have cables getting stuck and wrapped in places they shouldn't get stuck, things of this sort. So while it takes, let's say they're 0.3 seconds, the braking, stopping the system rotating, reversing the rotation direction, moving down, took usually 8 or more seconds. Right? This is why the later generations are going to try to avoid this problem. Because by the time this generation took over, your biggest slowdown, right? I mean, you're less than a second for the image, and then moving between slices, you know, you're say 8-10 seconds, right? So if you can get rid of that break and move and other things, you literally cut it down to 0.3 over 8.3, which means you're down to like 3.6% of the time. That's another huge increase. And it's all caused just because the large number of detectors, I got too many cables, I have no efficient way of pulling them off. So the cable becomes my problem. Another kind of nifty idea came in. So this has one big disadvantage, which I mentioned down here, right? The ring artifacts, right? So I mentioned the better collimation and stuff from picking the angle right to it, that they didn't mention, which I'm hoping that means they do, but they just didn't write it. The ring artifacts are huge though. Remember we talked about ring artifacts are kind of inherent to CP? They're really bad for this one. Because of the very geometry I'm using to fix this, it's going to naturally lend itself more to those ring type artifacts that's going in. One way I can solve that, right, because if any of them is off slightly in the calibration between them, certain brighter one, that's going to rotate around of who is brighter at the time. So, you know, miscalibration between your detectors will cause a bright spot that rotates around constantly, because as you move, the bright spot will move in a circle. Right? So they're never perfectly calibrated amongst each other, so they just naturally tend to have these type of artifacts, regardless of anything else going on. So the better way to do it is to get a very stable detector, but that's something you often have to now pay for, like a gas ionization chamber style as opposed to a crystalline scintillator. Crystalline scintillators are really fast, they're cheap, you know, they're small, things of that sort, but they're much harder to calibrate. The gas ones are really darn stupid stable, but they're more expensive, they're bigger, blah, 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 right? If I go to the fancier ones, I'm gonna get less of a ring artifact, but you can't remove it. I also have to calibrate these all the dang time. I'm usually having to calibrate them, depending on the system, at least once a day, sometimes multiple times a day, just to keep that ring artifact from becoming too, you know, oppressive in it. Now, this one is much easier to calibrate. You've got, since the actual detectors don't move, I make a ring of detectors. Originally, you had to have a really big ring because I put the source inside them and the source rotated. But since these are not moving, you don't get a miscalibration in one staying at a same distance away. So it moves out of there. So other ones are calibrated up or down, and so now they cancel. So this completely removes the calibration problem over here, right? Like if this one is off, right? That means this distance from the center is going to be brighter than everybody else if this tends to be a little stronger. Well, if this one's off and it rotates, only one thing is going to get hit by it. Because you rotate around, you use different ones. It was expensive though. Since these are not aimed at the source, you do not get this nice collimation, so you get more spreading. Right? Remember those angle spreads we had? You know, it's harder to put the grates and everything to cut them off because you can't aim it towards the source because the source moves. So it, you know, it makes a lot of those type of difficulties. It's essentially every bit as fast. It's a little bit blurrier. It's more expensive because of the images. It completely avoids the ring artifact problem. It also avoids the cable moving thing. So in between slices is actually faster on them because you're only moving the source, so you don't have to worry about the power cables. So that's much better on it. But overall, this was crazy expensive compared to this one just because of the number of detectors. And the benefits were not enough. So they came on, they were really exciting for a few years, and they died out because of the cost benefit. This, to me, the best thing to know about them is it was a cool idea, but it didn't consider the economics. And this is one of those underscoring areas. As an engineer, you gotta consider the economics. If it's too expensive, nobody buys it. Even hospitals we think of as wealthy. But it was a clever way to avoid the problem that the other one had. 5th generation electron beam scanner is not a classic system in the same way. It was a really clever idea. Right? It's a different way of building them because I don't have an X-ray source. So above your head, you actually have an electron gun, and I have basically a deflection system. 180 degrees without loss of generality. Let me see, it's the lower part. Right? Basically a tungsten ring, and I've got essentially a tube, usually evacuated, that's underneath on the bottom part, and I essentially deflect it and just scan it, the electron beam, along so that it targets an angled piece of tungsten. So this is kind of like making this whole part, the left and the bottom half, essentially becomes one giant X-ray source. Heat problem's gone, right? Because your actual X-ray source is here, right? That midpoint where that, along. So I'm just targeting there. I move down it, once you move past that area, as hot as it stupid wants, right? So I could run it really, really hot for an instant, and you're never going to get hit again for minutes, so you have lots of time to cool down. So I have no heat problems, essentially, with this design. I can be stupid fast. I mean, literally, it's in milliseconds that this thing will take a complete slice, not just an image, right? The upper half is detectors, so I get that whole, essentially, I get a complete image of you, and I'm not rotating anything. The only thing being swept is the beam. I can move that really fast. So I can take a complete two-dimensional slice of you in the time it takes everybody else to take one projection. Right? That is a ridiculously fast statement. Right? It is crazy, crazy fast. Right? So people sometimes call these like ultra-fast scanners, all kinds of stuff like that. Effectively, it is really costly, though. But this is one of those weird cases. It has not died. Right? It's always on the edge. But if you need something stupidly fast, and there's one case where you need something stupidly fast, anybody got to guess what that is? What part of your body would I want a crazy fast image of you, like fraction of a second? Heart. Exactly. It's used for cardiology. Yeah. So it's really hard to get rid of this because most people can't. Now, over the last, I'd say, decade and a half, people keep trying to come up with mathematical ways to allow the other ones to replace this, right? To be able to, in essence, invert that time axis. If you can do that, this technology dies, right? Because there's, at that point, you can use a standard machine and invert the time and away you go. So that's what a lot of 4D CT systems do. They try to capture many, many images, right? And then correlate them to your heart-lung cycle and then invert them. Does that make sense? So this is kind of a particularly neat situation. 6th generation is actually the first one on the original scheme that was truly innovative. And the real thing is the second point I have here, the slip ring, right? Where I comment about that kind of break on here. Think about what a slip ring is, right? I don't have to have a cable now. I've got rings and little brushes, and it rotates in the same direction. So now I can have a continuous movement of the bed the person's on, and a continuous scan. So I make a helix as it's kind of going down along the bottom. Right? I never have a stop. I never change direction. I'm constantly moving in the transverse. There is no break. There is no reversal. There is no transit time. I'm taking it continuous with the system. Right? The net advantage of this is it is insanely quicker than the rest because the time it takes to acquire a slice, it's ready instantly to acquire the next slice, as opposed to having a delay of, say 30 times a slice acquisition. So it's the same speed technology, but by removing the spacing between it, the magnet just operates continuously, it goes faster. Now, most of the time, there's a big disadvantage, right? Whenever I say there's a good thing that goes on, the first thing that should hit your mind as an engineer is there's a bad thing that goes along with it, right? So what do you think is going to happen to the image quality by not constantly looking at the same spot, rotating around? It would seem to make sense, wouldn't it? The really weird thing is your image quality gets better. I want that one to sink in for a second, because that's surprising, right? But it's actually been proved the quality of the 3D image improves. And the reason of this is, normally what you do in a typical CT is you capture a slice here, and then you move and you capture the next slice, and you stack them. Think about your inter-slice behavior. It can be very bad, right? I don't have any of that to carry. By doing a helix, I'm gathering the data in between. And I'm not grouping all things one way or the other. Therefore, it spreads it out. So it inherently is going to couple, and there's a lot of similarity. When you're taking steps that are, say, like, 0.0625, right? That's, 0.0625 millimeters is a pretty small step. But that's often, an inner plane size. And it's powers of 2 of that is usually what you get. But it's pretty tiny when you're getting down to it, right? So you take that 0.0625, and now you've got a little bit of an overlap that's within there. You'll get a couple, right? So you would imagine the geometry is pretty similar between these tiny areas. So, if you're catching part of a rib, you'll catch part of the rib in the next one. So it will actually be able to use that inner sampling between there to smooth it out. You actually get a better quality 3D image by doing a helical scan than you do by a point and sample, because you avoid that horrible inner sample problem, and you're able to spread them off each other. So essentially, 6th generation kicks the butt of anything before it. It is faster, it is better, just all around, you can't get it. It's sometimes called volumetric scanning. The one number you'll always hear from people on this is pitch. So I gave you here the most basic pitch, which is table travel over slice thickness. It's always table travel over something. Now, you can actually adjust, not just on table travel over the individual slice thickness. I can also do it over the reconstruction volumes thickness. So sometimes people, you could do it off the slice, and you can do it off how effectively wide the beam is. So those are the 2 ones that can go. So I could have, like, let's say I had a 1 millimeter wide beam, but I was traveling 1.5, or 1 centimeter wide, and I was traveling, you'll end up with effectively that, say 15 millimeters over 10 millimeters, right? 1.5 centimeters over 1 centimeter. So you'll get that pitch of 1.5. But that means I'm not sampling the whole thing. I'm only sampling part of it. But because of the overlap, I can often get the same quality as the original, but give you a lower dose thing. But that's on the reconstruction. I can then try to subsample that down so I can still have a 1-to-1 type of slice. So they can be different between how thick is my slice and how thick is the sampling beam that I'm using. That make sense? So when I go to 7th generation, what we do is we go to multiple detectors. So imagine that this one here shows 4. Usually it's either 64 or 128. Right? That's why the original one that came out were all 64, so they're often called 64 slice CT, even though some of them are 128 now. But in this case, imagine I have 4 of them. On the original system, see how long and thin they're shown here? It really was the same length. This one's just sliced up. Right? Now, the fatter they are, right, causes blur. Right? If they're taller and thinner, I can use more of the ones going through an area, and I can kind of average them out, bin them together. And because geometry for a narrow area, a centimeter or less, it's going to have a lot of similarity, I'm probably okay with the vertical area. So it allows me to go quicker without having to have as bad of a dose. So it's a little better for my source, it's a little better for the person and things like that. When we split it up here, really they stuck a lot. So if I have more efficient detectors, I can use less radiation to get them. I can separate those up so that I can catch multiple lines. Now, just because I have 64 detectors doesn't mean that I'll use 64 parallel planes for reconstruction. Very often they'll group them together, 1 at a time, 2 at a time, 4 at a time, 8 at a time, 16 at a time on the common groupings. And they put them and make a virtual one of these long things. So it's always in a column. You don't ever go the other direction. Because you go the other direction, you blur across objects, right? We're considering that our slices, right, are really axial slices when we build them. Right? So when we're doing those, right, the thickness between the slices is what we're choosing. If you bin more together, you have a bigger inter-slice distance. But oftentimes that's more than good enough. So I can do a faster one by grouping a bunch of them together and kind of averaging across the bins, effectively just add them together. So I can make a synthetic aperture that looks like the original. All right? But now I can software control it. All right? So the 7th generation just gives me flexibility. I will always get multiple of them, but I can adjust how many I group them together in software-wise to bin them, to be able to get some of the nice benefits of some of that, intersample behavior. So it allows me a software control for them. And since I'm still getting multiple ones at a time, often I'm getting 4 detectors at a time on these, because if I did 16 times 4 gives you 64, right, the number that's in there. Some of the newer 128 ones can give you up to 32 in a blend. But like, let's say I took 4 at a time. I'm still going 4 times faster than the 6th generation is. But now with more efficient detectors, I'm able to average those better. So I'm also getting a higher quality image with a lower dose. It's just all around win, right? Disadvantage? It's not a huge disadvantage though. So 7th generation is eventually going to replace 6. But there's still a lot of 6 out there. 3rd generation, you'll still find some old machines out of use. But pretty much everywhere, if you're building one now, it's going to be one of these, depending on where your cost point is for purchasing them. We feel good with these? Okay. Alternate types of scanners that are out there. We've mentioned cone beam CT before. So imagine I don't want to have to move. Right? So now I take a cone. I take an appropriate cone. I don't have to do. I take one slice. I'm taking the whole thing. So now I put an array of detectors over here, and I have a cone source going through. This is done in a lot of like dental stuff, but it can be in other areas for any reasonable section of the bite. And I just take one rotation, and I get a whole bunch of slices through the cone. Right? So effectively, I don't have to do the transverse part. So this has done a lot of stuff for head, other kind of stuff, right? Head, dental, things like that. So it's a one-shot deal, so it's even crazy faster. And essentially, you can do the same type of a process. You're just using the entire amount generated from that source. So it's a little more efficient on your source as well. Instead of having a fan beam, you're capturing the subsequent layers by the cone shape. Make sense? It's a pretty, the cone beam one is not a huge. The only difference you have is just because of the shape, right? You have some of the upper layers. You have, again, you just have to account for that when you're calculating the path trajectories. But other than that, the reconstruction will be the same. Okay. Last one, I'm going to talk about dual energy CT. I don't remember if the book talks about this or not, but this is a really hot new topic that's It also competes against some of the technology that I'm using, so I think it's worthwhile to understand the trade-offs of both. What they do, there's 3 different possible configurations of it, depends on the company, right? Copyrights win. So, one of them, one of the most basic ones you often see, is shown with a 90-degree separation. I just have 2 sources, 2 completely different detectors. So think of it just like a 3rd generation system, except with these 2, and now just rotate them. I could do the same thing for helical or anything else, but I just use 3rd because it's a simple idea to understand. Right? Obviously, you do the same thing with, if you're doing a 6th or a 7th generation, I can obviously do the same basic setup that's on here. But this allows me to measure at 2 different energies. We'll talk about why we want to do it later on. But since I'm getting 2 images, I'm not combining together. I can use less radiation per image because I can add the 2 images together. So it does not cost an effectively huge difference in the amount of radiation dose. It's very similar dose-wise, but I get 2 different energies. All right, so it's closer to 2 monochromatic sources. They're not actually monochromatic. There is some spread. All right, that's already taken. What do people have to do? They can't just change it a slight degree. So they put 2 right next to each other towards 2 detector planes. Sometimes they have the same detectors. They just make it a little wider, and one at one end, the other at the other end, and overlap them. Sometimes they've done them above each other. 2 different detectors calibrated for their own area, so you can exclude other ones. It's another way that it's kind of set up. And then you also have one where it's, you can see my double layer one is over here, right? Where that one's kind of done this way, front to back. All right, so instead of doing it on top and just having 2 different sources, I can have the 2 sources, I can put them front to back, and I use the front one as filter for the back one. So I only get the high energy ones. Because the front one detecting will remove some stuff, so I can kind of get an energy separation from them. So, and now all I have to do is turn on 2 different energies onto that. I just adjust the voltage across that, so now I can have 1 source, 2 energies. Yay. I just rapidly switch. Okay, that's what it is. Why would I want to do this? Well, the best way to understand it is down here. Right? We all know these lovely little attenuation curves that's going on. You know, here's an example, bone and iodine. This one shows one of the early systems at 56 and 76. Right? But the idea is going to carry the same whether. Most of the modern ones are 80, 140 or 70, 150. So, but you notice when I take 2 different samples, right? I get a sample of one particular energy and of another energy. Well, the attenuation curves are going to move, which means the images are going to change. So if I look at one particular voxel inside, and I look and see that, you know, I have an effective attenuation here for one and here for the other, that differential that comes in, right, a smaller change, tells me that had to have been bone. Whereas if I get this, I can identify that, oh, that was an iodine, which is where it's uptaken there. Same thing happens for soft tissue. If you've got enough of a spread between the energies so that the difference between your 2 measurements are large enough, it's the same thing we do with pulse oximetry, right? You just, it's 2 variables, 2 unknowns, solve for the dumb thing. You can find out the exact composition. Now, you've got an X-ray CT that's almost doing the same thing an MRI did. You can actually distinguish soft tissue. For about the same amount of overall energy cost, right, or dose to the person. That's a really cool idea, right? So it has huge advantages. I'll talk about, you know, PCT and some ion CT next week. But I want you to think about this. I can actually figure out materials off here. It removes a lot of those problems that goes on. And it's got, you know, a lot of high precision that's on here. And it's just directly taking advantage of those attenuation curves that were a pain to us before, but we've in essence taken something that was a pain and turned it into our advantage. Now, it does have some disadvantages. You know, there's nothing is perfect. And this is one of those cases you're going to get some trade-offs on here. You know, but the least I would say on this, I'll cover this, some of the disadvantages when I talk about the advantages of the PCT system that we'll do. But overall, it's a very clever design idea that allows you to essentially remove the biggest disadvantage of CT. In 2 weeks, we're going to do how to do the reconstruction. We'll start with filtered back projection. We'll go through all the gory details of it as far as we're concerned. But I just want in the last 2 minutes I've got here, I want to just give you a quick reminder. So everybody remember filtered back projection? Have you seen it before? Yes, no, some yes, some no. Okay. So you've essentially got a couple things we're going to do, right? You'll always see when you talk to doctors, medical things, they always talk sinogram, right? It's kind of funny to me because sinogram is just a data convention, how you organize your data. It really is just how did you store the damn raw data, right? But it is how everybody deals with it. You do have to understand how the data is stored to figure out how to then reverse the image. So that's kind of what the upper left and actually both of these pictures are trying to get towards. You can see that purple object in the upper left, right? You can see the point source is really just talking about, that was that point source we were talking about along with the object. It's not a true source in the sense it's not generating light, but it's the point everything's going through. Here it's assuming that we've got, in essence, parallel ones coming in. It's really not significantly different when we go to fan beam geometry or cone beam. So just imagine that I'm taking these. It's going to integrate all of those attenuation coefficients along, and we're going to get a net amount of losses. And that's the shape that's showing up there on the projection, right? So you've got the source on the bottom part going through lots of attenuations along the length, and you can see it. So where it's thicker, more gets attenuated, the way to go. Make sense? Okay. Now, that projection, literally, if you just turn the heights into numbers, gets stored in a row. That's all it's telling you, right? The S is just the directional or the distance along the detector plane, and that's what's being measured in your columns. Now, I have seen some systems where they flip this, the theta and the S. Okay. It's not magical. When you see the sign shape to it, you'll instantly be able to change, right? The direction of the sign shape is the theta direction, the other one is S. But there are some, and I've seen them go either way. Typically, when they're shown in most figures, they go this way. Anyway, you just get those rows. And then when you take it from a whole bunch of different objects, and I like this one just because you can imagine this is the center of rotation. I've got an object around it. So when I'm taking from this straight on, you can see it's centered on it. When I come from this direction here, it's below, so it's a little bit to the left, right, the next round. So you can see how the particular projection of this onto here moves as it goes through. The net effect, they map them over here, shows you doing that area. It looks like a sinusoid because it is a sinusoid. That's where the name sinogram came from. Now realize, I don't have to actually stack them this way. Right? It's naturally what kind of comes out of the machine when you read them time-wise. But there are other ways I could actually do it. And if I'm doing a helical scan, it's not as precise on this, to be very honest, because the travel down correlates with it. So you don't really get a straight one. And what happens if I do a cone beam? They overlap. So it's not as obvious when you get there, but you could always shuffle to this if you want to, or unshuffle. So it's been a standard configuration just to talk about. But just think about the data. I can always get back to the individual beams, and I can do everything from there. Does that make sense? Awesome. How do we undo it? All right. The upper line of that just shows them taking the images. And we already talked about this. This is just getting the storage. The most basic technique is filtered back projection. All right. So this one is just, there are 4 projections. It's really 2 projections, I think it, because honestly, they're identical, 180 apart. But you smear it back, right? You take that projection, smear, take the projection and smear, right? If I did it from 8, you can see it's going to overlap. this is not, they called it back projection. It's actually filtered back projection because you have to low pass filter it to remove the smearing is in essence adding low frequency because it's constant all the way across, low frequency. Right? So this creates, regular back projection creates huge amounts of low frequency noise. So you put a high pass filter on it, that's the filtered back projection. You get these sharper images. Right? And as I go to more and more, it just gets clearer and clearer. Right? How do we normally do this? We normally do it Fourier transform. They always talk about radon transform, but radon transform is just through the center. Right? So if you just ever remember central slice theorem, right? This is a picture of it. Imagine I took an object, I took its 2D Fourier transform, I get this. If I take a projection, right, here, take its 1D Fourier transform, at whatever this angle is here, same angle through the center, I'm going to get the identical shape. So I can therefore take these projections, their Fourier transforms, and just at each angle stack them up. I'll get a radial version of this, invert that transform, boom. You've got your image. So I can, the nice thing about this is essentially I can do a 2D Fourier transform or a 1D Fourier transform. Which would you rather do? Yeah, right, it's just faster. So the central slice theorem really imposes, you're crazy if you don't do it the 1D direction. That's kind of really the net effect of it. They are identical mathematically, and one is faster. Good? Awesome. Well, that gives you enough. That's the end for today. So we'll pick up next week with the particle ID.